Section 2.1, Displacement and Velocity. The objectives of this lesson are to describe motion in terms of frame of reference, displacement, time, and velocity, to calculate the displacement of an object traveling at a known velocity for a specific time interval, and to construct and interpret graphs of position versus time. First, we need to start by defining a frame of reference. And a frame of reference is a system that helps us to specify the precise location of objects in space and in time. Now, you may ask yourself, where have you heard of this before? And the first thing you might think of is thinking about when you're on a train. So when you're on the train, let's say that you're walking on the train forward at a rate of 5 miles per hour. But the train is also moving at a rate of 20 miles an hour. So here's the train. Probably looks like a tank or something, but that's not my train. And here's the person, it's you, on the train, okay, standing there. Now you're walking forward at a rate of 5 miles per hour, say, but the train is moving forward at a rate of 20 miles per hour. The train is on the tracks, and alongside the tracks, say, let's say there's like a road over here. There's a road alongside the tracks. Now, you could say that you are currently moving at a rate of 5 miles an hour with respect to the train, which means that you're moving 5 miles an hour, but you're on the train, or 5 miles an hour faster than the train is, which is true because you're gaining location. You're walking forward on the train. But if you were to think about your velocity with respect to the ground, you would say that you're moving at 25 miles an hour, simply because the train itself is moving at 20 miles an hour, but you're on the train already and you're moving at 5, so it really feels like you're moving at 25 miles an hour when it comes to the object next to you. Another good example of this would be like the conveyor belt walkways at the airport you see, where you get on the conveyor belt and you walk forward. So the conveyor belt might be moving at like 2 or 3 miles an hour, and then you're walking at like 4 miles an hour, so when you look to your left or right, it looks like you're like running almost. So it has to do with your frame of reference. So even though you're on the train is also moving. So really, with respect to the ground, your speed is 25 miles per hour. Okay, with respect to the ground. WRT, with respect to the ground. Now you're moving only at 5 miles per hour with respect to the train. Okay, so 5 miles an hour faster than the train. So keep in mind our frame of reference and consider the fact that we're really on Earth, which is always in itself rotating. The next term we need to define is our displacement. And remember that the displacement now is the change in the position of an object. The change in the position of the object. So in this case, we're talking about the final position minus the initial position. And we're talking about one-dimensional motion right now, so this is an easy example with this lizard here. The lizard has traveled from approximately, it looks like 23 on the stick. We don't know what the units are, but 23 units, up until about 83 units. So the lizard has moved around 60 units of length. And notice that the lizard is being measured from the same location. We could have done this. We could have said, well, let's measure from the tail to the tail, and we'll notice that that's about 60 units also. Or we could have measured from the nose to the nose, and that's also about 60 units. So either way we think about it, if we think about that blue gap right there, or that red gap right there, or the black gap that's been highlighted at the top, the delta x, again, is simply just about 60 units. So what we can say is that delta x, or the change in displacement, is really the final position minus the initial position. Now for this example, we see that a space shuttle takes off from Florida and circles the Earth several times. So right away, in your mind, here's the Earth, here's the space shuttle. Okay, so the space shuttle is flying around the Earth several times. It flies once, maybe twice, a few times. Let's see what it says. So it says it lands in California. And then it says, while the shuttle was in flight, a photographer flies from Florida to California to take pictures of the astronauts when they step off the shuttle. It simply says, who undergoes the larger displacement? Who undergoes the larger displacement? Well, in essence, this space shuttle might have flown a few times around the Earth, but then it landed in California. So let's say here's Florida. Oops. Let's say here's Florida and here's California on the Earth. Okay, so let's say the space shuttle started at Florida all the way back here, okay? Took off, it flew a few times around, but it landed eventually in California. So, it started here in Florida and ended here, even though it went around a bunch of times. Meanwhile, this photographer hopped on a plane in Florida and just went straight to California. But it says, who undergoes the larger displacement? It's a trick question, because in reality, they ended at the same location and started at the same location. So the displacement is identical. Remember, the definition of displacement is the change in position. It's not how far you've gone, that's distance. So, yeah, sure, this space shuttle went like 10 times around the Earth and landed. It flew a much further distance. The other guy just flew right from here to here. But the displacements are the same. So if I walk in, a totally different direction as you walk to get to school, but we both start at the same location and end at the same location, our displacements are identical. The next thing we want to think about is the simple fact that we can have positive and we can have negative displacements. So these are just 3 examples that are showing you on the left-hand side of positive displacement, something starting at a lower initial value and ending at a higher value. And on the right-hand side, we're seeing that if an object moves left, we can have a negative displacement. Okay, so again, positive or negative displacements. Whereas distance, the distance is always positive. The distance you travel is always considered to be positive. Okay, our next term here is average velocity. And average velocity is defined as the displacement of an object over a given time interval. So what we're saying is our rate, okay, a rate. So velocity is a rate. How do I know it's a rate? It's because it's divided by time. Whenever something's divided by time, it's some sort of a rate. So we have a displacement over time, so it's the rate of change of our displacement. So how fast are we changing our location or our position? And we'll notice that our displacement in this example is measured in meters and the times in seconds, thus giving us units of velocity of meters per second. Let's take a look at an example of average velocity. During a race on level ground, Jamie runs with an average velocity of 6.02 meters per second to the east. What is Jamie's displacement in meters after 2 minutes and 17 seconds? Alright, so right away we think to ourselves, okay, we've got an average velocity of 6.02 meters per second. Whenever I think of average velocity, I put a bar over it. The bar over the average, or over the V, just means average. Next it says that what is her displacement if the time taken is 2 minutes and 17 seconds? And we want to know what is the displacement. Well, in this problem, we have to think to ourselves, it doesn't matter where she started and where she ended. The displacement is just how far she's gone from the beginning to the end there, the change in her position. She's going in one direction. She's not changing directions. So I don't need an initial position and a final position. I'm really just looking for my change in position over a time period. So we can do that. Now, notice that the units of velocity are meters per second, so everything's got to be in meters and it's seconds, and that means that we need to adjust these units. If we realize that a minute is 60 seconds, we have 60 seconds here twice, which is 120 seconds, plus these 17 seconds gives us 137 seconds. Check that to make sure. So that's the time we're going to use. So let's take a look again. Our formula is velocity average equals change in displacement over change in time. Well, what do we want in this problem? We want the change in displacement. So let's get rid of the change in time. Notice that the change in time is currently being divided on the right-hand side, so let's multiply to get rid of it. Remember, in math we multiply since it's being divided, so we can multiply both sides by delta t. Well, what does this do for us? It cancels. We cancel both of those, just like we did with scientific notation and dimensional analysis. Now at this point, what we're going to see here is that we can just write our formula simply as delta x is equal to delta t times average velocity. We know the time period is 137 seconds. We know the average velocity is 6.02 meters per second. Notice the seconds cancel, giving us only meters for this example. Only meters. Final answer around, that's delta x again, so our final answer is delta x, canceling these units, is 824.74 meters. So when the problem asks, what is Jamie's displacement in meters, her overall displacement, or her change in position, is 824.74 meters. Now we need to talk about velocity and speed, and most people consider them the same thing, because in layman's terms you'd think they're the same, but in physics terms they're not. Now, in physics we already defined velocity as the displacement over a given time period. We talked about the average velocity of an object. So again, velocity is displacement over a given time period. Now, if we remember a minute ago, displacement indicates the direction that we went in. So displacement, we might say like left or right, being negative or positive displacements. Whereas distance, we go back to that term from earlier, distance, it doesn't matter. If I walk to the left 5 units or to the right 5 units, the distance I've traveled is just 5 units. Left and right makes no difference at all, but displacement direction does matter. So it's the same idea here now. For velocity again, we said velocity was defined as displacement over a given time period. But speed is going to be defined as distance over a given time period. Okay, again, distance over a given time period. Now what we have to do is recall that the slope of a line really indicates the steepness of a line, or the rate of change of the line. So rate of change, this is really analogous to velocity. We're going back to the idea of velocity, or rate of change of something. So if we think about it this way, we could say to ourselves, well, a slope of a line is the rise over the run, or the change in the vertical coordinate over the change in the horizontal coordinate. Well, if we think about this, as long as you make the vertical coordinate the displacement and the horizontal coordinate the time, we have displacement over time, which is our velocity. So let's take a look at an example of what we're talking about now. Let's draw a graph, and let's say that the graph looks like the following. We've got the position along this axis in meters, and let's say we've got the time along this axis in seconds. Let's say for the sake of this we have a simple example. Let's say this is going to be 5, and this is 5, this is 10, and this is 10. And what we notice is that we have a very simple example. Okay, so we have an increase of 5 units in both directions. Well, in this problem, we could take a look and say to ourselves, well, in a given time interval, we have a given amount of displacement. So here we have a 5-second time interval. If we go over, we have to go up here, we have 5 units of displacement. So this tells us that when we have a delta x of 5 meters along the y-axis, we have a time period that undergoes as 5 seconds. Well, by definition, the velocity is the delta x over that. Well, it's the same thing as finding the slope of this line. So really what we're doing is we're having 5 meters every 5 seconds, which gives us a average velocity of 1 meter per second. Well, 1 meter per second, 1 is just the slope of this line, really, too. I mean, we could pick another coordinate over here if you'd like to. Say 5, 5, and 10, 10, because that's what we have going on here. Now, if we find the slope, well, slope is change in y over change in x, so it's going to be 10 minus 5 over 10 minus 5, which is just 5 over 5, again, giving us 1. The same exact value as we had before. So here's what we can say. We can say that the slope of a position versus time graph, again, the slope of a position right here, versus time graph is the average velocity. Alright, we're just about done with this. Let's do one more thing now. Let's say we had a graph that looked like the following. We've got a line that is steady. Sorry, let me label the axes first. Position versus time. Units I don't care about. Steady line. We have a line that starts around the same way but decreases. And we've got a third line that has some sort of an increased direction. Well, what we can say right away is this. We could say that the dashed blue line has a positive slope, so it has a positive velocity. We could say that the solid blue line had no slope, so it's got 0 velocity, and we'll take a look at that. Let's take a look at that right now. Well, the position at the beginning of time, say this is 10 meters. Well, it starts at 10 meters. After 20 seconds, it's still, if we go over, it's still at 10 meters. The position is staying the same. It's staying at 10 meters. If you're staying in the exact same position, do you have any velocity? No, you have 0 velocity. And finally, the black line, clearly this person's or this object's position is decreasing, so it has what kind of a velocity? It has a negative velocity. Okay? Until it goes beyond here, it still has a negative velocity, but then it'll have negative position as well. Example 3. A book is moved on a table around the edges with the table dimensions 1.75 meters by 2.25 meters. If the book ends up at its initial position, what is its displacement? If it completes its motion in 23 seconds, what is its average velocity? And what is its average speed? Alright, so first we start with, if it ends up at the initial position. So here's the table. Here's a tabletop. Here's your physics book. And the physics book has been taken, has been moved here, then it was moved here, then it was moved here, and then finally back to its original position. So what's the displacement? Well, displacement is final position minus initial position. Well, the final and the initial position are the exact same location. So it has 0 displacement. So part A, displacement is 0 meters. Well, let's take a look at part B. Part B says find the average velocity. Well, velocity is defined as displacement over time. Well, it has no displacement, so it's going to be 0 over 23 seconds. So what's the velocity? The velocity is also actually 0 meters per second, which is crazy. Because you know it moves, so you'd say it has some velocity, but velocity, again, is displacement over time. Since the displacement is 0, it must have 0 velocity also. Here's the part that helps us make sense of this is speed. Well, speed is defined as distance over time. So yeah, the time is 23 seconds, but the distance traveled now we have to think about is this. 2.25 is this way, 175, 225, and 175. So if we add those 4 different directions up, we're going to end up getting a total of 8 meters. Now, if we know the total is going to be 8 meters over 23 seconds, and we divide those two, we end up getting a speed of around 0.35 meters per second. And that's the answer that we want to use for speed right there. 0.35 meters per second. Alright, let's take a look at number 4 now. 2 students walk in the same direction along a straight path at constant velocities, one at 1.5 meters per second and the other at 2. Let's assume they start at the same point at the same time. How much sooner does the fast student arrive at a destination 500 meters away? Alright, so in this problem, we're really thinking about a problem that has 2 different solutions, and those solutions are definitely uncoupled. And uncoupled meaning they're not related to each other. So we have to think to ourselves, we have a velocity of a first student that's an average value of 1.5 meters per second. And for the second student, we have a velocity of 2 meters per second. We know that both of the students have a displacement in this problem from the origin to where they end up of 500 meters away. So x1 is going to be 500 meters, and x2 is also going to be 500 meters. So what we can simply do here is find the time for each of these scenarios, the time it takes student 1 and the time it takes student 2, and then just subtract those times. So let's start with our generic equation. We have change in displacement over change in time. Well, the change in displacement is set already. We want to find the change in time, so let's solve for t here. Well, we can multiply both sides by delta t to start. So let's do that. So we have delta t times v bar equals delta x. And then in this case we can divide both sides by v bar. giving us delta t equals delta x over v bar. Well, that's the same thing if we had just gone back to the original formula and taken this and switched them. So remember, whenever you have this triangle situation for any set of variables, no matter what, you can always switch this way. Okay, these are the means and the extremes. These are the means, these are the extremes. So you can always do that. You can flip the means or you can flip the extremes. There's nothing here, there's just a 1. So here, we can flip these two, and that's what we end up getting over here. Well, let's find delta t for both these cases. So delta t for person, or the first person, is going to be delta x, which is 500 no matter what, over the average velocity. We'll say this is 1.5 meters per second. And then the time taken for the second one is going to also be 500 meters, but that's over 2 meters per second. So in these cases, we get 333.3 repeating, and it's going to be seconds. And over here, we end up getting 250 seconds. So if we wanted to figure out how much sooner the faster student arrives, we take a look at our time periods. 333.3 repeating minus 250, giving us approximately 83 1/3 seconds. Actually, exactly 83 1/3 seconds, I should say. Which is, in sense of minutes, because it's approximately 1 minute and 23 seconds. Again, 23.3 repeating. Practice problems pertaining to this topic are seen here.